All right, we have problem number 6 in group theory. If F is a map from Z15 to Z5 plus Z10 is a non-trivial group homomorphism, what is the kernel of F? We'll start with A. So we'll begin a proof environment, part A. And we want to know what the kernel of F is. And so we're definitely going to use first isomorphism theorem. So maybe we'll just get the phrasing out of the way. By the first isomorphism theorem, we have that Z15 modded out with the kernel of F is isomorphic to the image of F, which is a subgroup of our codomain, which is Z5 plus Z10. Okay, we want to think about how this is useful to us. Sure. So we have this first part, which is that Z15 modded out with the kernel of F is isomorphic to the image of F. And this first part is, what's the index of the kernel of F in Z15? If we consider orders, we essentially get the equation 15 over the order of the kernel of F is equal to the order of the image, the image of F. So we get this relationship. And let's see, we also know that the image is a subgroup of this guy, which has order 50. So by Lagrange, we know that the order of the image of F divides 50. Okay. By Lagrange, we know that the order, hence whatever we get from dividing 15 by that kernel has to divide 50, essentially. And so, of the possible divisors we can pick from are 1, 3, 5, and 15 itself. Let's divide 50. Okay. So, first of all, we can rule out the order of the kernel of F equaling 15, since the homomorphism is non-trivial, and that would yield a trivial homomorphism. Okay, and we can rule. Furthermore, we can rule out I'll say the kernel of F equaling 1 and the kernel of F, the order of the kernel of F equaling 5. Let me put the order symbol around that. If it was 1, then we'd have the order of the image equals 15, which does not divide 50. And if it was 5, we'd have the order of the image equals 3, which does not divide 50. Since 15 and 3 do not divide 50. Thus, the only possible order for the kernel of f is 3. I don't know why I said that. The only possible order for the kernel of f, I should use words there, is 3. Yeah. I suppose typing something different. Okay, and so the order of the kernel is 3. So this corresponds to, okay. Therefore, the kernel of f is equal to the cyclic subgroup for 5, of 5, which is, I mean, this is, I can be more explicit, this is equal to the set of 0, 5, and 10, order 3, yeah. Okay. So we did part A, now we have to do part B. Begin proof. It says, how many group homomorphisms G from, it's just the map, but the other way, are there? Okay, for counting group homomorphisms, we just have to consider, we consider the images of generators. Consider the images of generators. Maybe I'll do it like this. The images of generators 0, 1 and 1, 0. The images of generators. These guys. Yeah. Okay. So we know that 1, 0, so that 1 is in Z5, so 1, 0 has order 5. And, okay, but let's write this out explicitly. How do we want to phrase this? We'll say that we know that G of 1, 0, so the image of 1, 0 divides the order of 1, 0, which is equal to 5, and the image divides, let's see, what's our codomain? The image divides the codomain of Z15, and the image divides the order of, I'll say that, our codomain, which is 15. Hence, the order of G10 is equal to the GCD of 5 and 15, which is equal to 5. Hence, there are 5 possible choices. I believe it's 0, 3, 6, 9, 12. Yeah. Are they're the 5 possible images of generators there. Okay, that will give us group homomorphisms. We also considered the other generator. Further, we know that G of 0, 1 divides the order of 0, 1, which is 10, and the image divides 15. Thus, the order of G of 0, 1, let's see, is equal to the GCD of 10 and 15, which is equal to 5 as well. Therefore, there are times 5, there are 25 group homomorphisms for G. And that's that.